So today we continue on the third session on the topic on the limaçon, or as we mentioned, some people would call it the Limaçon. And we will cover mainly two aspects today. The first aspect would be why a Limaçon at a certain value of k, and we had talked about what the k is in the previous video, why it is called a trisectrix, and then we'll go further to look at a Limaçon or a limaçon as a pedal. So those are the main things we'll be looking at today. And so yeah, let's go on and cover these two topics. So we had drawn a limaçon as a set of points or a locus created by one end of a line that is centered around points on a base circle and rotated with a pivot set at point A. And this value of k here determined whether a limaçon or limaçon was a trisectrix or a cardioid or one that is just dimpled. We saw that obviously from this expression the Cartesian equation of the limaçon was radius equals to 2a, a being the radius of the base circle, 2a cosine theta plus k, and obviously the x value at point P, or point, let's just focus on point P, was 2a cosine theta plus k, all in bracket, times cosine theta, and y was 2a cosine theta plus k times sine theta. For when k equals to a, that was the radius of the circle, the limaçon was a trisectrix. And so looking at the equation, this would be the polar equation. So the question is, why the name trisectrix? So let's go further and elucidate why a limaçon would be a trisectrix when k equals to a. So let's assume we do have a base circle here, and we draw the diameter AB that passes through the center and touches the circle at point A and point B, and then we create an angle alpha. We draw an angle alpha such that BAR is that angle, and the length from A to R is equal to the radius. Let's be attentive here this time around. We're not using A as the radius, but R as the radius, and it's for a purpose that won't be apparent for now. But so we have radius R as the radius of the base circle. If we drop a line from R to center O, and we draw a line that passes through the point for which this line crosses the limaçon or the limaçon, angle theta is a third of angle alpha. And that's where trisectrix comes from. In other words, by drawing a line that passes a point for which the line from R to O crosses the limaçon, we are trisecting the angle alpha. So let's show why theta is a third of alpha, or alpha is 3 times the angle theta. So let's go ahead and join point Q, the point for which this line that crosses the trisectrix at this point where R is drawn to O, or the center of the circle. This point Q, let's draw a line from Q to O. And obviously, since AO equals to AQ, we have an isosceles triangle. In other words, the best angles are equal. So the angle OQA is going to be theta. And so since the internal angles of a triangle add up to 180 degrees, the angle up here is going to be 180 minus 180 minus 2 theta, right? And it is also important to note that since we had said that a trisectrix happens when K is equal to A or R in this situation, from here to here is the same as from here to here, and this K was supposed to be here, which is equals to R. So in other words, this distance is also going to be equal to R. But since we know this is R, we do have another isosceles triangle here. In other words, the best angles are going to be the same. And in that scenario, sorry, we mislabel here. This is 180 minus 2 theta. This angle here becomes 90 degrees minus theta over 2. Why? Because 180 degrees minus theta is going to be equal to the sum of the best angles, and then I divide them by 2. You have 180 minus theta over 2. Now this angle here now is going to be equal to 180 degrees minus 2 theta minus 90 degrees minus theta over 2, which obviously we have forgotten 2 here, which means that this angle here is going to be 90 degrees minus 3 theta over 2. And since this is the radius, this is the radius, this angle also is going to be equal to 90 degrees minus 3 theta over 2. And what does that mean for us? What does that mean for us? It means that alpha is equals to 180 minus twice 90 degrees minus 3 theta over 2. Okay. And that is going to tell us. So now, since we do have this isosceles triangle, these sides equal, the best angles are going to be equal. So what that means is that alpha plus 90 minus 3 theta over 2 plus 90 minus 3 theta over 2, where we'll just bunch that into twice that, equals to 180 degrees. And so that means that alpha plus 180, 2 multiplied by 90, minus 3 theta equals to 180 degrees, and these 180s cancel out. So in other words, alpha is equals to 3 theta. And that really is the basis for which we say that when k equals to the radius, we used a initially and then we used r, but when k equals to the radius of the best circle, the Limaçon or the Limaçon becomes a trisectrix. And so yeah, so now let's go and see one other thing. Why is a Limaçon a pedal of a circle? So let's go ahead and look at that aspect of things. So what is a pedal? And this is just in regard to a Limaçon being a pedal. So if we have a curve C and we have a tangent at point R, and obviously we might have several other tangents at different points. If we pick a point P, the projection from this arbitrary point P to that tangent, such that it is a triangle to the tangent causes this point x, right? We create a point x. So a set of these points x from the projections of this p to the different tangents that we can plot on this curve C is these are petals. So a limaçon is a petal, and probably it makes sense from you looking at what a pedal of a bicycle looks like. It's that device, or more of a part of a bicycle that is a triangle to a shaft that connects to the hub of a bicycle. And it's, if you could use that to help you kind of internalize what a pedal is. So we're going to use that to plot out a limaçon from a circle. Okay. This is going to be easy. We're going to start with a base circle, and then we're going to divide the circumference of a circle into multiple number of points, and we're going to plot the tangent. So we're dividing this base circle into a multiplicity of points that are equally spaced from one another. So the center point to that circle is shown here. We have A, B, and so we have about 40 points that we're going to create equally spaced from one another on the circumference of this circle. And then we're going to create an arbitrary point. Like we said, P was our point in the previous circle curve we saw. This time around, let's create a point A that is an arbitrary point here outside the circle. And so we'll begin by drawing a tangent to the first point here. And so as you can see, the perpendicular projections to these tangents, we're going to put the dots, the red dots. As we plot all around the circle, you can see that this perpendicular projection from point A to the tangents is tracing out a limacon or a limaçon. Right at the edges here, we'll see that this projections are not being drawn. I think it's because the gradient is just so stiff that the program can't get it right. But as you can see, as we draw these projections out, it traces out a limaçon just from the red dots that we've created. This point can be moved up, or it could be moved on this other side, and still the perpendicular projections to the tangent still will trace out a limaçon. So let's see in that situation. So you see here, we've moved the point up here, and then when we plot, as you can see, it still traces out the limaçon. The orientation of the limaçon is a little bit different from what we saw previously, but still the perpendicular projection to the tangent of the base circle ends up being a limaçon. So we're having a small issue here, but I'm thinking it's just a bug on the program, but still we have a limaçon being traced out. Let's try to see if we move the point down here. So we moved the point down here. Let's see how that pans out. So as we see, the vertical perpendicular projections they're tracing out a limaçon. The orientation of the limaçon is obviously different, but you can pick an arbitrary point outside the circle, and that perpendicular projection to the tangents of the circle will give you a limaçon. Obviously, how far out that arbitrary point is to the circle will determine whether you get a trisectrix or whether you get the loop of the circle is the inner loop is bigger, and how big it is. That is determined by how far out the point is. Again, this point here is a little bit wonky here. I feel like that's the program, a little bit messed up, but we get the general idea that a limaçon is a petal, and it's a petal of a circle. Okay, so that kind of covers what we wanted to deal with today. I hope you picked up something from our video today. If you have any question, feel free to leave a comment. But other than that, if you haven't subscribed, we do encourage you to subscribe to our channel. Leave a like or share it. Till next time, bye bye.